friends, welcome back to another session on multi-threading. Now let us see some issues related with threading, the process management. So the various issues to look at is about the fork and execute system calls, cancelling the thread, signals handling, thread pools, thread specific data, and scheduler activations. So let's see one by one. So when one thread calls a fork, then there are two possibilities. One is immediately after the fork is called, there is an execution exec system call, and this will replace the parent code from the child code. It will not allow the child to continue executing the parent code. It will have its own new code. But if there is fork and there is no exec followed, then only one thread continues to work. So when we call this in the multi-thread environment, if the fork is called and it is followed by exec system call, then all the threads are duplicated. If it is not followed by exec, then only one thread gets duplicated. Now what happens is when fork is followed by exec, that's a recommended way of working with the fork, and it's safe also. So after the fork, the child process immediately calls an execution system call to replace its entire memory image. So that means whatever parent's memory image was there, it will be totally replaced with a new image, and all the threads and resources are reset, so it avoids problems like deadlocks or inconsistent states and so on. So one thread calls a fork, then other threads, if they are allowed to continue, then they may hold some resources, and because of that holding resources, it won't be able to release them, then a deadlock or inconsistent state occurs. So we recommend to use exec system call immediately after the fork in the child process, so that a new memory image is created for the child. It is very safe in the multi-threaded environment and used in servers, shells, and multiprocessing frameworks. Say here, somewhere above we have initiated a fork statement, and if that is equal to 0, that means the PID is equal to 0, which means it is talking about the child process, and the moment it gets in, the instruction is executed to list the directory. So here the child does not continue with the original thread logic, it's a new code is used for that. But if the fork is used without execution, then it is very risky. The child process continues running the same code as the parent code, and only one thread survives. Now what happens when one thread calls a fork? Then that thread gets a duplication, and because it is not continued with the exec, therefore no new environment is created, and only that one thread continues to exist, and all other threads just stop working. And if other thread had logged any of the resources using mutex, then that will remain in the log state, and there is no chance of unlocking that, because the thread which has logged one resource is no more existing, because another thread has called a fork and it has created its own duplicate. and it is running that, and that duplicate never knows that other threads were also existing from the parent thread. Along with the parent thread, other threads also were existing, so that is the child process. Child thread doesn't understand, doesn't know, and hence there is no chance of running them, and hence the resources that were logged by other threads will remain logged forever, and that definitely will lead to inconsistent or partially updated state, and may in future get into a big problem like deadlock. Yeah, these all issues we consider when we look into our next series, the next module, when we look with memory management. So this can lead to deadlocks, race conditions, or crashes. Anything can happen. So it is always recommended when a thread is forking itself into another child thread, better use a exec command immediately after the fork, so that the child will create a new environment and other threads continue to exist, and they get their chance to run as and when the scheduler allows. So this is a example. If the fork is equal to 0, that means we are not using exec command here. That means the same code is being run, so can create many problems in the multi-threaded environment. So 4 plus execute, the child replaces itself with a new program. It is safe. Use cases will be shells, web servers, multiprocessing, and all that. If you want to use fork only, then child will continue to run the current code itself. It's definitely not safe in multi-threading environment. It is used in experimental or legacy code and all. Looking at the other perspective, the fork only way of creating new thread and fork plus exec way of creating new thread. So the code executed by the child is the one same as the parent was executing, whereas here the code is replaced with a new program. Use case for fork only, the multiprocessing with the same code, and fork plus exec running a different program. Memory space, it is copied from the parent, but in this case it is replaced entirely. Example will be the background workers in a server for the fork only, or fork plus exec shell launching a new command. So that's an analogy. Imagine a team of workers building a house, that is a process. If you copy the house and replace all the workers with a new plan, that is exec, everything starts fresh, no problem. But if you copy the house and let only one worker continue, then other tools are and incomplete tasks remain, causing chaos. That's what we are trying to say, that each worker was doing their own work, and if you keep only one worker continue to work and stop all other workers, then other activities get stopped and it remains incomplete, and definitely creating a problem. Then there is another issue of thread cancellation. This is a method to terminate a thread before it has completed its task, and it is typically done by another thread in the same process. So one thread calls for cancelling another thread before the other thread completes its job, and this is used when that task is no longer is needed. So if we think that the task that the particular thread is doing is no more required, then instead of keeping it alive on the memory and all that, we can just kill it and cancel that, so memory will be made available for some other actions. Or maybe because of timeout, another process like a scheduler may call to terminate a process, or application is shutting down. So main application is shutting down and that application has created many threads, and when the main application, that is when the process itself is getting terminated or shutting down, then the all threads also must terminate. So the threads get cancelled. So there is one thread which is responsible for cancelling all other threads at the time when that process is being terminated. We'll take care of shutting down all the threads one by one. So that's thread cancellation. And there are types of thread cancellations. One is asynchronous, that is the target thread is immediately terminated. The moment we say stop, it stops working, and this can lead to resource leaks or inconsistent state, because when we say stop, we are not sure that that particular thread is using some resources and all. It has locked some resources for its usage, and without releasing them, if we stop it, then it's going to create a problem, and definitely it is not recommended. So it is like cutting the power mid operation, so it just hangs there whatever had happened. There is another one which is called deferred cancellation. Here the target thread checks periodically whether it should cancel itself or not. So if somebody says to cancel, then whatever work it is doing, it will first complete that and then cancel itself. And this one is the safe and the recommended method of cancelling any thread. So it works only at the cancellation points like read or sleep or thread test case. So this is a default way of cancellation is the deferred cancellation, and it is always safe and recommended. So that's a example. So now going into another issue, that is the signal handling. A signal is an asynchronous notification sent to a process by to notify it of an event. A signal is an asynchronous notification sent to a process to notify that some event has occurred. Like if we press Ctrl C or some alarm timeout and all that, signal has to be sent to the process, and that is sent through signals. And these signals allow the operating system and other processes to interrupt or communicate with the running process. So when a signal arrives, the operating system will interrupt the current process or communicate with the running process. So how it is done? So first thing is a signal is generated, and then the operating system delivers the signal to the target process, and the process after receiving the signal may ignore it. If you can allow to ignore, then it may be ignored, or it may use some default action. Whenever that signal is generated, one default action is written. So every time the signal is generated, that default action takes place, or some custom defined handling action is taken. So that is a custom signal handler is run whenever we get a signal. So various functions. There is a signal, that is to register a signal handler. Seek action is the most powerful. The POSIX complaint handler setup. Raise sends a signal to the current process. Kill sends a signal to another process, and alarm triggers SIG alarm after a delay. So SIG action is the most powerful handler setup. Raise sends a signal to the current process. Whichever process is running currently, signal is sent to that. Kill, wherein we say which process to be killed by sending a signal. So this signal goes to that another process whose PID is written here, and then will kill that process. So alarm in seconds, then the trigger is activated after that delay. So the various possibilities. The default here, the operating system has defined the action. Ignore, just neglects the signal, or customer handler, you can call your own function. Then when it is multi-threaded, we have options: deliver the signal to the thread to which the signal applies, deliver the signal to every thread in the process, or deliver the signal to certain threads in the process, or assign a specific thread to receive all signals for the process. So when we are working with multi-threaded environment and we get a then the process gets a signal, then what can we do? So that signal may come with a label that this signal is meant for this particular thread. In that case, it applies only to that particular thread. Otherwise, the signal may be applied to every thread. So some signals are like emergency siren should be applied to all the signals in the process, all the threads in the process, or to certain threads in the process we can apply, or make one thread to receive all the signals of the process. Here there is one signal coming in and there are multiple threads, and signal may come with a tag about which thread it is sent to. So first one says applies to only that particular thread. Second one says signal comes, all threads respond to it. Another signal comes, certain threads respond to it. Or instead of keeping all threads waiting for signals, we can make one thread just to wait for signal and then take appropriate actions in for all the other threads. So two-level signal delivery. The signals are sent to the process, so sent using kill or the rise. Then signal can be handled by any thread that has the signal unblocked, or signal sent to a specific thread. Here the signal is sent to the process, whereas here it is sent to a specific thread. So we are using a p thread kill. Here it was just kill, and only that specific thread receives and handles the signal. So the best practice for dedicating signal handling thread: so block all signals in all the threads, create one thread with signals unblocked, so keep only one thread that can receive all the signals, and use sigwait or sigwait info in that thread to wait for the signals. So this way what happens, all other threads can safely continue doing their task. They don't have to wait for signals. So this way we can ensure that the signals reach one thread and only one thread will be waiting for the signals, and once the thread gets the signal, then it will inform appropriate thread what to do and all that. Then we have something called thread pools, a collection of pre-created threads that are reused to perform multiple tasks instead of creating destroying threads every time a task comes in. So yes, that's another issue. So every time we have a task, one thread has to be created, and when that work is over, that thread has to be destroyed. Instead of creating killing the threads, we can keep some threads pre-created and reuse them as and when required. The advantage is it reduces the overhead of creation and destruction and prevents resource exhaustion, because we want to have limited number of threads. Then this limited number of threads we can pre-create and keep using them. Then this resource exhaustion can be eliminated. Then improves responsiveness and latency. supports the task queuing and load control. Then we talk about something thread specific data that allows each thread to have its own private copy of a variable even if all threads use the same key or identifier. Yeah, each thread can have its own private copy of a variable, and in multi-threading global variables are shared by default, and thread specific data lets each thread store and retrieve its own value without interfering with others. Yeah, we would like to ensure that each thread works independently without disturbing others. So there something called global data which every thread can share, and that's what we talked in the beginning when we were talking about multi-thread system, that the data has one copy of data is available and all threads will use that. But here we add one more a small private data for each thread to store its own values. So this is useful while logging, it is useful while error handling, and used as a thread local buffers and re-entrancy. So whenever we want to repeat anything, then we would like to know where we had stopped and where to start and all that. Then we have finally scheduler activations, a mechanism that coordinates between the user level thread library and the kernel level scheduler. So this allowing efficient and flexible thread management to many threading models, as we have seen in the previous session. So there are some threads at the user level and there are some threads at the kernel level in the many model, many multi-threading model we have, and there is a mechanism required for scheduling which user thread should use which kernel thread and all that, and to make sure that it is efficient and flexible, scheduler activations are required. And here the kernel provides a virtual processor to the user space, and when an event occurs like a thread blocks, a new processor is added and the kernel notifies the user thread library via a scheduler activation. So whenever any event like a thread is blocked, then the kernel will notify the user thread library via this scheduler activation that something is wrong. So user thread which was allotted a kernel thread has stopped working, so it informs to the thread library that this particular user thread is no more working. So next time when you are trying to schedule it, make sure not to schedule that particular user thread and all that. All these things are done through the scheduler activation. So these are some issues related with multi-threaded systems. So that's it for now. Thank you.